Okay, so just to talk about biofuels for maybe the next hour. Okay, future hydrocarbon fuels or future fuels will come from many sources. Some petroleum will still be available. We'll have oil sands, oil shale. We'll have coal to liquid, Fischer-Tropsch. We've gas to liquid, hydrogen. We've bio-derived fuels, ethanol, butanol, algae. Sorry, this is just Fischer-Tropsch actually. Some different Centrolium, Sasol, Shell, Sasol Oryx, and Sasol Oryx isomerized. And all of these are fuels composed exclusively of either iso or mixtures, sorry, of iso and N-paraffins. Okay, some of them have more N-paraffins than isoparaffins, but mostly actually they're a lot of isoparaffins in them. Okay, that's the Fischer-Tropsch. And there are other ones that stem from other sources, I think, like alcohol. So if you have sustainable aviation fuel, you have alcohol to jet fuel, and then that contains not only N-alkanes and isoalkanes, but cycloalkanes and aromatic species as well. All right. So anyway, and just see. But anyway, the bio-derived fuels are ethanol is being used a lot, butanol, and then fuels derived from algae, and then you have biodiesel from vegetable oil and animal fat. So they're methyl esters typically. Okay, so we need to understand the chemical kinetics of these fuels, how they're going to behave in engines and in mixtures with conventional fuels. Okay, and we need to understand their ignition delay time, their cool flame, the reactivity, the extent of conversion, and what kind of product and pollutant formation is going to come from them. Okay, so I won't talk about that. You can. This is a slide that is from a paper that I was a co-author on with Charlie Westbrook in 2006. But actually, the idea was first published by Miyamoto et al. In an SAE paper in 1998. And what he did was he looked at the percentage of fuel carbon converted to soot precursors on the y-axis versus fraction of oxygen in the fuel biomass. And essentially, when you get to 20% oxygen in dimethyl ether, it's all dimethyl ether. Okay, right? So when you get to this point here, it's all dimethoxymethane. Here, it's all methanol, and so on. So it's just showing you. But the point of this slide is to show you actually where you have fuels and dimethyl ether is one of those, where you have no CC bond, actually you don't get soot formed. Okay? So you need to have CC bonds in fuels to generate soot. And having an oxygen atom in the molecule actually helps reduce the quantity of soot that's produced from the fuel. That's just really the point of that slide. Right. So what are oxygenated fuels are maybe syngas, you've got bio oil, you have alcohols, ethers, esters, ketones, furans. So they're essentially any of these fuels with an oxygen atoms in them. Right? And then you have to deal with the functional group and what effect that has. So this is a slide that was kindly given to me by Tiziano Faravelli. So he took as a baseline calculation N-butane. And these are quantum chemistry calculations. So the bond association energy here should be 101.1 or 101.5, as I said to you. But in this calculation, whatever he used, it comes out to be 99.7. But this is our default bond association energy for a primary CH atom in the molecule. A secondary is 97.2. I told you it was 98. So the calculations here are slightly lower than what they should be, but it's just giving you a kind of baseline, right? So just take it at that value. So, but if we go to N-butanol, so we have, again, 1, 2, 3, 4, and now we replace one of the hydrogens with an OH group. And that OH group has a profound effect. So here's the carbon to which the oxygen is bonded. But that CH bond now is no longer 99.7, it's 93. So the the bond association energy has decreased by 6.7 kilocalories per mole, making this CH bond quite weak, right? The other bond strengths are similar, right? Okay, this CC bond is weakened, right? That's what is it, beta, the bond beta to the OH. Okay, is it alpha or beta? I don't know. But anyway, and here we have an aldehyde. Here, when we have, this is a C double bond O, and when we have an aldehydic hydrogen atom, that's 12.2 kilocalories per mole weaker than a typical CH bond, or a primary CH bond, right? And so this one is very easy to be abstracted. Actually, the ones next to that are also weaker, right? But the weakest is the aldehydic hydrogen atom, right? If we look at the ketone, again, the hydrogen atoms bond to the carbon, which are alpha, the carbon which is alpha to the bond, so this one is also alpha, okay? This is weakened by 10.1 kilocalories per mole. Here, in an ether, they're lower by 6.6 kilocalories per mole, right? Because that makes sense. The carbon is bonded to an oxygen atom. The oxygen atom draws electron density away from it and weakens the secondary hydrogen atoms by 6.6 in this case, okay? And also the primary hydrogen atoms are also weakened by about the same. Well, it's 5.6, not 6.6, okay? And then in the ester, here we have C double bond O CH3, and again the methyl radicals here, the methyl hydrogen atoms, sorry, are weaker by 2.5 kilocalories per mole, but these ones bonded next to the ether functional group are weakened by 7.7 kilocalories per mole. So if hydrogen atom abstraction is occurring and the bond association energy is very weak, that's the hydrogen atom that will be attacked. And that's the radical site that will be formed in each of these species. So that will be the important one. And so if I just, and then that affects the reactivity. So if we take N-butane and we just take a model and we look at the predicted reactivity as a function of inverse temperature, so low temperature, high temperature, long time, fast time, you can see we have the NTC region. But N-butanol, right, is slower at low temperature and then faster in this regime compared to N-butane, right? N-butanol, here's the predicted reactivity, and in all cases is predicted to be faster than N-butane. This is just based on a chemistry model, right? We don't have any experimental results here. This is methyl butanoate, and you can see that there's lower reactivity at lower temperature. And then the reactivities tend to converge at higher temperature, right? But it's certainly affecting the reactivity, having these different functional groups on the molecule. That's the point of the slide, right? So if we look at alcohols, and I'll be coming back to this a little later, and this is the predicted reactivity of N-butane. The most important reactions are the ones with the thickest arrows. And what you see here is you've got the N-butanol molecule. The most easily abstracted hydrogen atom is the weakest one, which is the one bonded to the carbon next to the OH, right? And we form this radical that adds to O2. We get the RO2, and that undergoes a concerted elimination. Like I told you yesterday, based on the calculation, who was it that did it? I can't think. It was Joe Bazzelli and somebody else, right? Anyway, to give the aldehyde plus HO2, okay? And that a concerted elimination, I can remember the activation energy is 11.4 kilocalories per mole, okay? So that is the most important channel here. Now, the other ones can occur, so you can get abstraction here too, here, and here. They're all included, like 1, 2, 3. And then they can occur. But because this is the most important radical formed, a lot of the flux is going to go through here. It's going to form the aldehyde plus HO2, and this doesn't go to chain branching chemistry. So the reactivity of the alcohol is going to be predicted to be lower than that of N-butane. And you see here, N-butanol is slower to react than N-butane in the low temperature regime. Okay, we'll come back to that later. So what about ketones? We have something similar. Again, the carbon atom, which is bonded to the carbonyl group, the bond strength of these is 10 kilocalories per mole lower. The bond association energy is 10 kilocalories per mole lower than it would be for a typical secondary CH bond. And again, there's two important radicals here. The most important one is the secondary. So the primary here is lower by 5.2 kilocalories per mole. Secondary lower by 10. Why that is, I don't know, to be honest with you. You'd expect both of them to be about the same. But regardless, this is a primary and this is a secondary. So by default, the secondary will be faster anyway, right? But so you'll get formation of this secondary radical and also then the primary one, and then, sorry, the primary one, and the primary on the other side, which would be a typical primary alkane, right? But this species then adds to O2, and then that isomerizes back to give methyl vinyl ketone plus HO2. Again, it doesn't go to branching. You're getting this ketone plus HO2 formed. And if we go through this species here, this leads to the formation of this cyclic tetrahydrofuran 3-one plus OH radical. So it's like a cyclic ether plus OH reaction. Okay, and so, and also this species can go to methyl violet ketone also. But it's the fact that these reactions occur because of the functional group means that the branching pathways aren't as competitive as they would be normally. And it's going to inhibit the reactivity of these fuels. Okay, and here's, for ester, we see something similar. Okay, so in the ester, the bond strength, where are we? The bond strength, I should be looking here, of this secondary CH next to the ester functional group is lower by 7.7 kilocalories per mole. So definitely this radical will be the one that's most favored. Okay, so this one. Why? Because you get like a resonantly stabilized molecule. So this is like a C double bond C, except it's a C double bond O, right? And then you're abstracting the hydrogen atom from the carbon that's next to that. So now you're getting this resonance structure formed, and you get methyl crotinoate plus HO2 from that. And it doesn't go to branching. Okay, so hence the ester is going to be less reactive at low temperature compared to the corresponding alkane. Right. So this is interesting just to talk about the aldehyde also. So if we have an aldehyde, here we have 1, 2, 3, 4 C double bond O, and then there's a hydrogen atom here. That hydrogen atom is the most easily abstracted hydrogen atom. And so typically the branching ratio for this radical, or this one, is 80-20. So the predominant radical formed is this CO with the radical site here, right? So this will be NC4H9O, or NC3H7CO radical. But when this radical forms, it's very unusual. And this is something worth remembering. We have 1, 2, 3. 1, C, C, C. Where am I? C. Okay, so we have C double bond O. Okay, and we have this radical here. All right? And when that forms, right, we don't get beta scission. So this bond is alpha to the radical site. This bond is beta. We don't get this, right? That doesn't happen, right? It's very unusual, or it's not this beta scission that happens. This actually gives you C, C, C radical plus CO. Always. So when you have an aldehyde, the aldehydic hydrogen atom gets abstracted, and then you get the smaller alkyl radical plus CO. Always. Okay? That's what happens with aldehydes. Okay? And you can see here, look, we're just comparing the rate constant for H atom abstraction, a primary H atom abstraction in propane. This is the rate constant. But if you abstract the aldehydic hydrogen atom from butanol, the rate constant is way faster. Okay? Why? Because the bond association energy is so much lower, it's so much faster. That's why. Okay. So I'm going to come back to these. I'm going to follow those in a second, because here I'm going to talk about propanol isomers. Okay, and this is taken from work that I published 16 years ago. Okay, and here we looked at the oxidation of isopropanol and N-propanol. So here you can see the black data are data for the black squares are experimental results for isopropanol. The red circles are experimental results for N-propanol. And you can see we have exactly the same composition of fuel, oxygen, equivalence ratio, and pressure. Okay? And what we see is that at all temperatures, N-propanol is about a factor of 2 faster than isopropanol. Right? So why is that? Okay? So if we take we have a model, it doesn't show it, but the model was able to match the data, or we made the model match the data, okay? And if we do a flux analysis at the same condition, so 0.5% of we have the same amount of fuel, same equivalence ratio, same temperature, same time of conversion. So at the time of 30% fuel conversion, what's happening to the fuel? And what we see for N-propanol is that 29% of the fuel undergoes an elimination reaction forming propene plus water. I'll show you that in a second, right? For isopropanol, the fraction is more than double that. It's 63%, right? So we're getting twice as much, or a little bit more than twice as much propene plus water from isopropanol compared to N-propanol. Now, when we produce propene and water from a molecule, will that be reactive? Will that give us reactivity? Okay, no, because we're not getting any radical species. You see, these other reactions, we're producing radical species. We're getting 2 stable molecules from the fuel, okay? So that's not going to help us, right? And that happens twice as much in isopropanol compared to N-propanol, and hence isopropanol has half the reactivity of N-propanol, or N-propanol is twice as fast to ignite as isopropanol. Okay, I said it in a very roundabout way, but you can see what I mean. Okay, and that's essentially what's happening. So they're competing reactions. The most important reaction inhibiting reactivity is the reaction of the fuel giving propene plus water. That competes with this other reaction which promotes reactivity. Okay, and if we have something similar for N-propanol. N-propanol gives propene plus water, inhibits, but if it gives you ethyl plus hydroxymethylene radical, it enhances, because we're getting 2 radicals here, we're getting 2 stable molecules there. Okay, makes sense, right? But this reaction, right, has only half the amount of flux going through it for N-propanol compared to isopropanol, right? So why? Okay, so if we look at it, we have N-propanol goes through this transition state. So there's a 4-membered transition state ring, which leads to the formation of propene and water with a rate constant here. Now, note this rate constant doesn't have an activation energy. How much, if I go back, you see here, these CC bonds have activation energies of 84, 87, 86, 82, 84. They're in the 80s, right? So that's the activation energy to break those is going to be in the 80s, right? But for this concerted elimination reaction, the activation energy is only 67.3, okay? Much lower, right? And the frequency factor is reasonable as well. And it's a unimolecular reaction, right? So these happen much faster than other CC and CH bond breaking reactions. The activation energy of the CHs is going to be 101, 98, 96, up in that range, okay? The CCs. COs are actually lower, okay? So anyway, you see the rate constant for the formation of propene on water from isopropanol is faster than that compared to N-propanol. We have the same activation energy, but the frequency factor is about 7 times faster in this case compared to this case. Now, part of that is due to fitting. Okay, I put my hands up. But part of it is also due to the fact that here, in this transition state, right, we only have, how many do we have? This is CH2C. This should be CH. Okay, apologies, this should be CH, not CH2. Okay, so we only have 2 hydrogen atoms here. In isopropanol, we have 6. So there's a degeneracy there of 3 just from the number of hydrogen atoms available in the transition state. Okay, so you can see here we've got 6 equivalent hydrogen atoms. Okay, in N-propanol, this should be a CH, not CH2. That is only 2. Okay, so based on degeneracy alone, the frequency factor for isopropanol should be 3 times that of N-propanol. And we had to use a difference of close to 7 to get. So it was a factor of 2 adjustment. Okay, but in doing that, then we got agreement. Okay, so another thing I want to say about this is, though, the unimolecular rate constant that we estimated was estimated based on the work by Wing Zhang, published in 1976, right? So we used that 20, 30 years later. But the rate constant that I used, or we used in our model, right, was this magenta line. That rate constant was actually measured here at Princeton by Josh Hine, okay, and published in 2015, okay, and I was actually a co-author on that work, okay, and here's the here's the 2 points that he measured for that rate constant, right? I'm not trying to say, look, we were great and we published the right rate constant. That's not the point of this. The point that I'm trying to make is that from the data that we had to use that rate constant to get good agreement of the ignition for the ignition delay times. And when we did that, it forced us into getting a rate constant that was very reasonable, right? That's the point, okay? So, and you can see how well they agree. So then this is a plot, this is isopentanol, this is what the molecule looks like. And this was studied back in 2011, 2012, maybe about a decade ago now. But there's efficient production routes from biomass to its formation, and it has favorable characteristics as a homogeneous charge compression ignition fuel, okay? So this is just showing you the heat release rate as a function of crank angle degree. The dashed line here is for gasoline. The blue line is for ethanol, and you can see that the blue line doesn't match the gasoline line, but actually the isopentanol one does very well. So it's a very good surrogate for gasoline, right? So its low temperature heat release and so on is similar to that of gasoline. So the idea then is Well, we better understand its chemistry, okay? And we should study it, okay? So it was actually De Silva and Boselli, okay? So I have this slide again, okay? And you can see that this concerted elimination reaction, just reminding you of it, so the most easily abstractable hydrogen atom is that alpha to the alcohol functional group. We get the peroxy radical, we get this chemically activated intermediate, and that gives us concerted elimination to the aldehyde plus HO2 in an alcohol. So this is for ethanol, but this can be any R. And so for isopropanol, we can have something similar. We took data to simulate, we studied this in our shock tube and RCM. So these were actually RCM data taken by Professor Jackie Sung at the University of Connecticut, and these are our shock tube data taken in Galway. And you can see that for all these three conditions, 0.5, 1, maybe a few rich conditions were a bit slow, but we're capturing the data quite well. Is there anything in particular that you notice about these data, though? Just very quickly off the top of your head. About the shape of the curve in comparison to that for N-pentane.
There's no negative temperature coefficient.
Yes. There's little or no negative temperature coefficient. There's a little bit of a bump and so on, but you don't see the NTC behavior that you did for N-pentane, right? So there's a lot less low temperature reactivity going on because of that, right? So why is that? Okay, and it's because of this. So if we take, this is isopentanol, we abstract the hydrogen atom here, the most easily abstractable one, we form this radical, the RO2, and that gives us, with the same rate constant as for ethanol, because this is, instead of having a CH3 here, we have this group here, but otherwise it's the same as ethanol, right? And we then form this aldehyde plus HO2. And we have the same rate constant for that as De Silva and Boselli calculated for ethanol. Okay. Now, this molecule can also, so this has an activation energy here. So, but we could have, we have an available hydrogen atom here. I've drawn it this way, okay? So if the OH was oriented this way, it would form this radical, okay? But the activation energy of that reaction is 20 kilocalories per mole. It's 8.6 kilocalories per mole higher than this channel. And at low temperature, 8.6 kilocalories per mole. Can you calculate what 8.6 kilocalories per mole is at 600 Kelvin? So, I don't know, don't do it now. It's the exponent of minus 8,600 divided by 1.987 times 600. Okay? And whatever that is, but it's going to make this channel uncompetitive with this one, right? Assuming that the frequency factors will be somewhat similar, okay? And why would there be 1, 2, 3, 4, 5-member transition state ring here, and here you have 1, 2, 3, 4, 5, 6-membered ring? Okay, it's a 6-membered ring. But if you did the 5-membered ring on this side, 1, 2, 3, 4, 5-membered ring, okay, you could get isomerization to give the 5-membered ring, but the 5-membered ring activation energy is going to be 30 kilocalories per mole. So the difference there will be 18.6 kilocalories per mole. And what's 18.6 kilocalories per mole in activation energy is 600. It's going to be prohibitively, it's not going to be an order of magnitude anyway, it's going to be many orders of magnitude difference. Does everybody understand what I'm saying in terms of the rate constant? Okay, so in other words, the only game in town really, once you form this guy, is this aldehyde plus HO2. The other possibilities won't be competitive in rate constant. Okay, and so, okay, I won't go into it. Well, okay, I just wanted to, I just say okay, it's not the only radical that you can form. You can form this radical too, right? When you form that radical, you get this alkyl peroxy radical, and then that can isomerize to form this one, okay? But again, this will give you isobutylaldehyde plus formaldehyde plus OH, because you have the radical site here on this oxygen atom. Can we add O2 to this species to get an O2QOH and branching? No, because the radical site is on the oxygen atom. And because the radical site is on the oxygen atom, O2 is not going to add to that. It's going to be repelled, right? So it won't form an O2QOH, right? Because the oxygen atom is actually going to be repelled because the radical site is on the oxygen atom. Okay, and again, if we form this radical, but if we don't abstract the alcoholic hydrogen atom, but we go the other side, there are actually 3 available hydrogen atoms via a 6-membered ring that we can isomerize to form this hydroperoxy alkyl radical, which is like a conventional alkane hydroperoxy radical, which can add to O2. But again, the activation energy for this channel is 24.4 kilocalories per mole, calculated at the same level of accuracy as this one, which came out at 22.2 for this one. Okay, so again, the activation energy barrier, okay, for this is 2.4 kilocalories per mole higher than it is for this one. Okay, so it's going to occur much less. Okay, it's not going to be as competitive. Okay, so that's alcohols. Okay, let me just move to ethers then. So that was alcohols at both high temperature and low temperature. What about ethers at high temperature? This is a very nice study by Kenji Yasunaga. He actually came and worked in my lab for 2 years. He works at the Ministry of Defense in Yokosuka in the south of the bay from Tokyo. Okay, and I went to visit him a couple of times there. But so the default data are these black bullets, right? And their ignition delay times taken for 1% hydrogen with 1% oxygen and argon at a pressure of about, I don't know, 1.8 on average, plus or minus, okay? The pressure is varying from 1.4 to 2.6 atmospheres, right? And then what he did was, he said, okay, let's take 0.9% or 90% of the hydrogen and replace 10% of that hydrogen fuel with another component, okay? So he replaced it with isobutene, methyl tert-butyl ether, ethyl tert-butyl ether, diethyl ether, and ethyl methyl ether, okay? And he had these the square data here, and then he had these triangular data here, okay? And actually the square data and this open symbol data, the open bullet, are all very similar, okay? So what it's saying is, look, if 10% of hydrogen is replaced by isobutene, methyl tert-butyl ether, or ethyl tert-butyl ether, that inhibits reactivity considerably. If it's replaced by diethyl ether and ethyl methyl ether, it's inhibited at the lower temperature range, right? But it actually enhanced at higher temperature. So what's going on, and what explains this chemistry, right? So again, it's our good old molecular elimination reaction, 4-centered, the same as the alcohol. But this time, the activation energy barriers are slightly lower, right? For the alcohol, it was 67 kilocalories per mole, now it's 60, right? And here we have NTBE, the rate constant is 1.7 times 10 to the 14, 60, and we got isobutene plus methanol, okay? So methyl tert-butyl ether is going through this 4-centered elimination reaction, giving us isobutene and methanol. And then ETBE does something similar, right? But it gives you isobutene and ethanol, right? And so on. but the rate constants are the same, right? And so, because MTBE and ETBE are both giving isobutene, if we go back one, then the effect of isobutene, MTBE, and ETBE on hydrogen is both the same, right? And they're all inhibiting. Why? Because we're forming isobutene and methanol and ethanol, right? What about isobutene? When it forms, right, and it's going to be oxidized, the only, well, the hydrogen atoms that are easiest abstracted are the allylic, primary allylic ones. But once we abstract those allylic hydrogen atoms, apologies, right, we get this resonantly stabilized radical, which is long-lived and is going to inhibit the reactivity of the system. So forming isobutene from either, well, itself as a fuel or from the ethers leads to inhibition, because it's going to give you resonantly stabilized radicals once you abstract a hydrogen atom from it, okay? And then you're going nowhere fast, right? And hence the inhibiting effect of all of these. So MTBE and ETBE behave like isobutene because the fuel essentially becomes isobutene and methanol or ethanol, right, very quickly, right? And then all of the reactivities have the same effect on hydrogen by inhibiting it, because you get a resonantly stabilized radical from the fuel immediately, okay? So, but for ethyl methyl ether, ETBE can also proceed through a 6-membered ring, forming ethylene and terbutanol. I'm going to be quick about this, but ethyl methyl ether and diethyl ether both also go through a 4-membered ring, giving ethylene and methanol and ethylene and ethanol respectively. So EME and ethyl methyl ether and diethyl ether both form not isobutene, but ethylene and methanol and ethanol, right? So actually, if we go back then, it means that ethylene must be slower than hydrogen at lower temperatures, but faster than hydrogen at high temperatures, right? So let's just look at this. This is a calculation I had somebody in my group perform for me, and it shows that ethylene is actually very fast to ignite. So what we did was we took at 1 atmosphere pressure an equivalence ratio of 1 in air. I asked, please calculate the ignition delay, predicted ignition delay time. There's no experimental data here, right? So what we're seeing is, look, propene is slowest, then isobutene, and this is a modern, result. Then we have propane, then we have isobutane, then we have ethane is faster, which you'd expect. But look at ethylene in comparison to ethane. It's even faster again, okay? And what happens with ethylene undergoes H-atom abstraction, and you get vinyl radical. And that reacts with O2 to give CH2O plus HCO at lower temperatures, and then CH2CHO plus O at higher temperatures. Okay? I spoke about that yesterday, right, in the lectures. And that's a very important chain branching. Both of those are very important chain branching pathways, one at lower temperature and one at higher temperature, for vinyl plus O2. And systems are very sensitive to that, right? So when Franklin Goldsmith and Stephen Klippenstein published that work, I was really excited to take their calculations and put it into the mechanism, right? Because that helped a lot in predicting a lot of reactivities that we had missing for a long time. But I was trying to tune the model to best match experimental data rather than have a fixed calculation of that. Okay, so but it's because of this reactivity. It's sort of like H plus O2 in many ways. It gives you so much branching, right? So it's a very important reaction in combustion. For me, maybe think of it as the second most one. Okay. All right. So, and you can see that ethylene is it's even faster than ethane, right? Which I showed you earlier in the week. Methane being the slowest, ethane the fastest, and the others in between. Okay. And that's what you see here again. Okay. So the production of ethylene in the case of those ethers then makes them faster, right? And then, so if we compare the reactivities of the alkenes at high pressure, okay, so this is at 30 atmospheres. Here's the predicted reactivities now and calculated reactivities with a more modern version of the mechanism than the slide I just showed you. This is for propene and isobutene. And you can see propene and isobutene have about the same reactivity at high temperature. Why? Because if I just that's isobutene and that's propene. Okay, very similar structures. Okay, isobutene has 6 equivalent hydrogen atoms here. Propene has 3. But once we abstract one of those hydrogen atoms, we get a resonantly stabilized radical. And when we get the resonantly stabilized radical, it's going to be long-lived, and hence propene and isobutene are much slower to react compared to the other alkenes. Okay, that's just a slide to kind of hammer that home. Here's ethylene and all the other ones are all here. So they're all quite reactive. Okay, so this was just saying again, I showed you initially the alcohol high temperature and low temperature. At high temperature, the molecular elimination reaction, and then at low temperature, that elimination to give the aldehyde plus HO2 doesn't give you as much branching. Okay, for the ether, at high temperature, molecular elimination reaction gives you the olefin plus the alcohol, and depending on what olefin you get depends on the reactivity. Okay, and then at low temperature, you can have similar chemistry to alkane, like I showed you earlier today, dimethyl ether. Okay, but this is, okay, and there's the dimethyl ether data stemming from that, which we published in collaboration with Fred Dreyer here at Princeton University 20 or 30 years ago. Okay, but this is something hot off the press, okay, and this is actually currently just still in review with Combustion and Flame, right? And I think it's very interesting, right? So let me go back a bit. So here we have, this is dimethyl ether ignition delay time, and then the prediction is the line here. And this is, so let me go here. Okay, so we have COC. Okay, that's dimethyl ether. Okay, and then we have propane, which is okay. So all we're doing is we're changing the central atom from a carbon atom to an oxygen atom. Okay, and if we do that, we see a huge change in reactivity. Dimethyl ether is way faster, maybe 2 orders of magnitude faster than propane in the low temperature regime. Okay, they approach one another at high temperatures, but dimethyl ether is still a bit faster. Okay, is that all right with everybody? See that? Okay, now we have a study. We just submitted it. It's in review in Combustion and Flame. It should be accepted soon. Okay, I hope, right? And here we have ignition delay times measured for 2,2-dimethylbutane and 2,2-dimethylpentane. And this is for MTBE and ETBE. So let me just draw those on the board. So MTBE is this structure here. Okay, ETBE has this structure. Okay, and then 2,2-dimethylbutane is that structure, and then 2,2-dimethylpentane what is it? Has that structure. Okay, so again, if we compare this and this, all we've done is changed this carbon atom, exchanged this carbon atom with an oxygen atom. And if we compare this and this, we've swapped. Okay. Is that okay with everybody? All right. But so in the case of dimethyl ether is 2 orders of magnitude faster than propane, right? You do the same thing for the ethers, right here. These are the alkanes and these are the ethers. The ethers are actually 2 orders of magnitude slower than the alkanes, right? So here the ether is 2 orders of magnitude faster, and here it's 2 orders of magnitude slower, right? Doesn't make sense, okay? Because we'd like a rule of thumb to say ethers are always faster or ethers are always slower. But actually, here now, it's changing, right? And it depends on the chemistry, okay? So let me just show you. So I wanted to highlight it and just to say, you cannot just say, oh, this is always this or this. We have to actually explore the chemistry. And the devil is in the chemistry, okay? And the detail of the chemistry. Okay, so if we look at, and here now, this is methyl tert-butyl ether, and then this is 2,2-dimethylbutane, okay? And what we see is that we get a radical, okay? And we get this TC4H9OCH2 radical. But most of this radical undergoes beta scission to form formaldehyde and tert-butyl radical, right? Why? Because this CO bond is weaker than a CC bond, okay? I think I mentioned it already earlier today, but I didn't. CH bonds are the strongest. Well, among these bonds, CH is the strongest. Then CC bonds are next, okay? And then CO bonds are weaker, okay? Sorry. No, I have to go back a lot. Sorry. Go back to those diagrams that... here. Okay, so our CC bonds are 87, 88 or so. CH bonds, they're around 100. And then the CO bonds, 81, 82. Here we have CO. Okay, so they're lower than the CC bonds. Okay. And so instead of going to add to O2, this radical, most of it undergoes beta scission, okay, in this case. And then, so the result of that is only 11.2% of the ETB that starts to be oxidized ends up to chain branching, okay? For its corresponding alkane, 59% of it goes to chain branching, okay? It's much more, all right? And it's not just that beta scission. So the beta scission, this is the rate constant for beta scission here at 700 Kelvin. And you can see for methyl tert-butyl ether, it's about 3.5 times faster than it is for the alkane radical, okay? It's not just that, okay? It's the fact that actually here, when you have the oxygen atom here, okay, and you form this radical. So let's just we form this radical, and then we have a hydrogen atom here. So we can have a 1, 2, 3, 4, 5, 6, a very fast 6-membered transition state ring from this RO2, abstracting this hydrogen atom, going on to form the hydroperoxy alkyl radical, the QOH. Okay? In the case of MTBE, that's not possible because it's an oxygen atom that's there. So there's no there's no hydrogen atom here that can form a 6-membered transition state ring to give you that QOH. And remember I said earlier that the 6-member QOH rings, they're the ones that mostly go to chain branching. They're the ones that give you the carbonyl hydroperoxide and the chain branching at low temperature. And just because of the oxygen atom then being proximate to the tert-butyl group in both MTBE and ETBE, they have similar reduced reactivities in comparison to the corresponding alkane, right? So that explains MTBE and ETBE in comparison to their alkanes. What about dimethyl ether? Okay, and sorry, here's, I don't know if this was in your thought, but here I just show then, we have MTBE, this is MTBE compared to its corresponding alkane, 2,2-dimethylbutane, and then this is ETBE in red compared to its corresponding alkane, 2,2-DMP. Okay, and what we see is if we do a flux analysis at 30 atmospheres, 5 to 1, and a temperature of 720 Kelvin, what we see is that, okay, we form the alkyl radical, and then 40% of MTBE and 41% of ETBE go to beta fission, but only 6.5% and 14.2% of the alkanes do that. Okay. Whereas if we look at R plus O2, 58.5% and 56.4% of the ethers go to RO2, but 93% and 85% of the alkanes do. Okay? And now the alkanes are on their way to low temperature branching and reactivity, and the ethers are much less on their way. Okay? And that's why they're slower. Okay? If we then look at propane and dimethyl ether, the opposite is true. So for propane, the only radical actually that leads to branching in propane is N-propyl radical. Isopropyl radical doesn't give you branching, right, for propane. And hence propane is quite unreactive because, again, the secondary site, the one in the middle there, that's the easiest one to form. It'll be the predominant radical formed, but actually it won't go to branching. But the N-propyl radical one does via this 6-member transition state ring. So a hydrogen atom here, we have a 1, 2, 3, 4, 5, 6-member transition state ring, but the activation energy is 24.8 for that, giving us this QOH, hydroperoxy alkyl radical. In the case of dimethyl ether, though, this hydrogen atom is weaker. It's more easily abstracted because it's bonded to a carbon which is bonded to this oxygen atom. This oxygen atom draws electron density away from the carbon towards it, weakening the CH bond. And so now the activation energy for the transition state here is only 17.7, not 24.8. And we form the QOH. So it's much easier to form the QOH. And all of the radicals, there's only one radical in dimethyl ether. This is it. In propane, there are two radicals, N-propyl and isopropyl. And actually isopropyl is at least 60%. So at the start, you only have about 40% of the fuel flux leading to the QOH species. But not only that, it's much slower because the activation energy barrier leading to it is much higher. And hence dimethyl ether is much faster, or propane is much slower than dimethyl ether at low temperatures. right? Because of that, but again, it's down to the chemistry. But it can be explained quite logically and rationally through the chemistry that's happening. Okay? But it takes quite a bit of detailed analysis and understanding to know what's going on. But it makes perfect sense when you think about it. All right. So what about esters? Okay, so here we have a large ester. So this is the kind of ester that would be formed from the biofuel, biodiesel, okay, or in biodiesel. But so what we did was we looked at the functional groups of esters. So here we have methyl ester, and here we have ethyl ester. Both of them have the molecular formula C5H10O2. Okay, but they have different reactivities. So again, similar to the alcohols, what we found was ethyl propanoate is always about a factor of 2 or more faster than methylbutanoate at the same condition, right? Consistently. Why? Right? So here, if we look at the fuel flux for the fuels at the same condition, what we find for methylbutanoate is that we have radical formation and H-atom abstraction and some decomposition reactions all happening, right? The usual suspects, right? But actually, ethyl propanoate, it's dominated by this 6-member transition state ring, okay? Because we have the ethyl group here, we have an available hydrogen atom. So if think of one of these hydrogen atoms on the methyl group. So we have 1, 2, 3, 4, 5, 6-member transition state ring formed, and it leads to the formation of propanoic acid and ethylene, right? With, again, a Ray constant which has an activation energy barrier that's very low. This time it's 50 kilocalories per mole, right? For the ether it was 60, for the alcohol is 67, but unimolecular decomposition reaction, again, has a minimum of about 80, right? So these are really low activation energy barriers, and so they're going to go gangbusters, right? And they're going to be the only game in town at high temperature. There is a kind of a similar transition state that could happen for methylbutanoate, but its Ray constant isn't competitive with the other decomposition reactions, so it doesn't really happen. Okay, so the thing is, when you have an ethyl ester, and it has to be ethyl, because then you have this CH2, CH3, right? That can now form this 6-center transition state ring. It doesn't matter what this group is, right? And you're going to get the corresponding acid and ethylene, always, with a Ray constant that looks like this, always, for an ethyl ester. And ethyl esters will always give you the corresponding acid and ethylene, always, okay? And then go on to react, right? So something similar to like ethers, okay? So that explains then the difference between, if I go back, sorry, here we had ethyl propanoate is giving you ethylene and the acid. And what did I say about ethylene in terms of its reactivity? It's fast. So ethyl propanoate is faster than methylbutanoate because it's eliminating, giving you ethylene, which is fast to react. Okay? And that's why we see that. Okay, good. Okay. So one thing I just wanted to point out here, and again I'm running out of time, okay, is if we look at, here we have propane, okay, it's CH3, CH2, CH3, okay, that gives us negative temperature coefficient behavior, okay, and we see it here, okay. But if we have methylbutanoate at low temperature, so see here, we have CH3, CH2, CH2. So if you consider this molecule here, or this part of the molecule, it should, you would think, behave like propane. Then it's bonded to the C double bond O, OCH3. But remember earlier, I should have moved that slide and I apologize. if I go back. No, I have to go back a long way. Sorry, you guys. Where are we? Esters. Yeah. Okay. If we abstract a hydrogen atom here, we then get the formation of methylcroton-OH plus HO2. And that's going to inhibit reactivity. Okay? Whereas in propane, if we abstract the hydrogen atom there, that eventually leads to chain branching. Okay? But in methylbutanoate, we can't get that chain branching because we're getting the formation of methylcroton-OH plus HO2. So we can't get the branching happening. Okay? And when we can't get the branching happening, we don't see low temperature reactivity like we do in propane. And that's the point of that's the point of these slides. Sorry. Okay? We don't see. So you see the reactivity only starts to kick in at about 800 Kelvin. We don't see any NTC behavior or anything. And actually, if we look at methylbutanoate, a similar condition compared to methylbutanoate, you can see we have the characteristic negative temperature coefficient behavior. Okay? And actually, methylbutanoate seems to be faster at the higher temperature compared to methylbutanoate because it's actually inhibited, or sorry, compared to butane, because it's inhibited in the NTC region. Okay. Okay. And then what about large methyl esters? Actually, looking at the ester functional group doesn't matter a jot because these molecules behave like large alkanes. And they really behave like, you know, as if this was endodecane or something like that, or I don't know, like a C16 alkane. This behaves like a C18 alkane. This behaves like, well, this has one double bond in it, this has two double bonds in it, and this has three double bonds. So remember I said that this side here is a superallylic because there's a double bond either side of it. Okay? So if you look at soybean oil and rapeseed oil, and you form esters from either one of these, you can only make any one of these 5 esters that will be used as biofuel. So these 5 are the 5 potential biodiesels that will be used, right? And Cherry Westbrook did a calculation, this is the result of it, ignition delay time plotted here on the y-axis versus inverse temperature. And what you see here, the fastest molecules to ignite, both the C16 and the C18 with no double bond in it, have the same predicted reactivity, okay? And then the species with one double bond has a reduced reactivity because of the double bond. We talked about that earlier, okay? And the one with the 2 double bonds is next slowest, and the one with the 3 double bonds is slowest again. So the double bond in the molecule will inhibit its low temperature reactivity as the olefinic chemistry is inhibited, okay? Because they are essentially olefins, right? And so what's controlling the chemistry is the alkyl chain, not really anything to do with the ester chain, okay? Okay, and I already spoke about that, okay? And one last slide as I finish this. This is a really nice slide that I've never published, and I would like to publish maybe at the symposium coming up, right? So actually, the chemistries of alkanes, alkenes, alcohols, and aldehydes are all interlinked, right? And so if we look at butane, for instance, we abstract a hydrogen atom, we form this radical, the RO2, and that RO2 gives you olefin plus HO2, right? So the olefin in this case that we've drawn is 1-butene, right? So actually, alkane chemistry and alkene chemistry are linked through the alkyl radical, and then it reacts with O2, you get the olefin plus HO2, okay? Then the alkene chemistry, if you take an alkene and you add OH radical to that, okay? So we add an oxygen atom to this carbon atom, we get this alcohol radical. Okay? This is the radical that you would get from an alcohol, right? M-butanol. Okay? So actually, alkene and alcohol chemistry are intrinsically linked, right? And then if you take the alcohol and you have some reaction, that will produce aldehyde, okay? And then the aldehyde, we abstract this hydrogen at the aldehydic hydrogen atom, we get this radical, and then that decomposes to give N-propyl plus CO, okay? So you can see this circular economy, or whatever you want to call it, right? You've got alkane linked to alcohol, and then you get the aldehyde. And then the aldehyde can decompose to give the smaller alkane. So it's a bit of a spiral down. But all of these chemistries are interlinked. And I haven't seen anyone yet, ever, take one model and prove that that one model can simulate all of these moieties simultaneously, right? But if you can, it proves that you understand, and we understand, the intrinsic chemistry controlling all of the species simultaneously, and that the chemistry is right. Okay? So you'll see models in the literature that will simulate alkanes, and other ones they'll simulate alkenes, other ones will simulate alcohols, other ones will simulate aldehydes. But I've never seen anybody publish a model to simulate all of them together. So that's what I want to do at the next symposium, to show that. To say, yeah, we do understand the chemistry, actually. And if we can do it, it's evidence that we do understand well all the chemistry and how they interact. Okay, so let's call it a day at that, and we come back at 20 to 5